So one of the workshop ones we did was what I called it a sugar derivative. I think I put an OH over here and an OH over here. And I said if you have some H plus around, what are you going to get? So what's going to happen here, first step, using a strong acid to protonate our carbonyl, make it a more reactive carbonyl, the carbonyl group. This is kind of that Fisher projection type look. This is not a real sugar. I think they don't have methyls like this, but whatever. And then you have a choice. Now you have an activated carbonyl, the carbon of the carbonyl. So the question here is what alcohol is going to attack. You can either do it intermolecularly, where another molecule comes around, or you can try to do it intra. If you're going to do it intra, you want to be thinking about 5 and 6 member rings. Right? Anything less than that or more than that, it's not going to work. So let's see if we count 1, 2, 3, 4, 5. So that seems reasonable, have that oxygen attack. So I'm going to kind of redraw this now to make it a little easier to deal with. But since I've numbered my carbons, it should be fine. So this was 5, 4, 3, 2, and 1. And so if you look at it, 2 has just 2 H's on it, that's fine. 3 has an OH, and 3's OH and the OH on 4 are on opposite sides, right? So it doesn't really matter which way I do it as long as they're on opposite sides. So if I make this OH wedged, I need to make this OH hatched, right? Or you could do the other enantiomer as well. Doesn't matter. All right? So cyclized up. Let's see, I forgot to, there's still an H on here. I need to balance my charge. There should be a plus charge there, right? And then, of course, this H plus is a catalyst. So the last step will be regenerating the catalyst. And the final product would be the cyclized sugar. And these are actually methyls there, so I should draw those in as methyls, I guess, if you want to be picky. There you go. Feel better about that? Somebody will want those there. There you go. And you obviously made H plus again. Retrosynthetic problem. The start material is this. Do I have too many carbons? Nope, that's right. That's our start material. And they're saying working backwards, what is this from? Right? So we're going to have to work backwards. So you have to start recognizing some pieces here. The first thing I would recognize, so they give you some options what's possible, but if I'm looking at it, I got to figure out, so I have an alcohol, a tertiary alcohol, right? Everybody see that? Tertiary alcohol. Does this tertiary alcohol have 3 different things bound to it? No. So it either comes from a ketone or it comes from an ester, right? Right. So if we want to add one thing that's different, right? And the ring thing kind of looks weird, right? You guys, I mean, it's harder to make rings. So the bond you want to think about breaking, where this came from, is that. But there's a problem, right? You guys know how to make carbon-carbon bonds. What's the major way you guys know how to make carbon-carbon bonds? It's either Grignards or what's the other way? The first way we learned. Alkynes. Remember the alkyne, the terminal alkyne stuff? Maybe. See, if you take a step back, right, it couldn't have probably been that. It had to have been this first. Now, some clues to this problem. There's some clues in this problem, and that are, if you look at, so this is there's narrowing your choices, right? If it was me giving you a problem, you could do it a lot of different ways. But they're kind of narrowing your choices. And it's pretty much indicating, if you look at the possible options, that you have to go through an alkyne to make this carbon-carbon bond, if you look at the options. So let me make sure I draw this correctly. Let me clean it up a little bit here. All right. If I number these carbons, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, and 7. All right. So we're still looking at breaking this bond here. And that would have came from a ketone. Maybe a negative charge in the end there. 1, 2, 3, 4, 5, 6, 7. Right? Because one of the options you could actually use is cyclohexanone. So that's one of your options as reagents. So now the question then becomes, if we keep working backwards, is how do I build up this? All right? How do I build up that? Well, one of the start materials, I mean, they could have told you started was from acetylene, right? So it's that 2-carbon piece. So if I want to build up that from acetylene, what do I need to do? So this can come from acetylene. There'd be an H, but so what do I need to add to make that from acetylene? If I'm working forward now, I would need to add Na, NH2, right, to deprotonate it. And then I need to add what? Where would there be a substitution at? What would I need to add? Exactly?
Carbon 3 will be bonded to bromine.
There it is. Right, because we're just going to do an SN2 then to get that. And then we need to add, moving forward again, we need to add NaNH2 again, right? Because that's going to deprotonate right here, which will give us this, which can then do the addition here. So the step 1, right, is the addition. Step 2, we add H+, right, to protonate the alcohol. And then the final step here, just palladium, H2 palladium ion carbon, right? We'd get it all the way down. It's a tough one, to be sure. It's one of the ones where you probably want a clue that says start building off the out. You start with acetylene, right? I usually give you a starting material to start with. All right, now we're going to look at what if we start off with the acetal. What if I want to get this taken off? How would I get it taken off? Well, you'd use actually the same reagents you use to put it on. All right, because these are equilibrium reactions, right? So in this case, instead of using a bunch of alcohol, we'd use water, right? So the first step is going to be protonation. It doesn't matter which one we pick. Right, so now it's like having a reverse tetrahedral intermediate with a good leaving group, right? So if we have a tetrahedral intermediate with a good leaving group, we want to bring our lone pairs down to kick it out. And we just lost methanol or ethanol there. So now we say we have an activated carbonyl, carbon of the carbonyl. So now we'll grab some of our solvent. Right. That adds in. Forms a tetrahedral intermediate. Tetrahedroimmediate, we ask ourselves, what's our best leaving group? If it's the same thing we just added, we want to do a proton transfer. So let's do that. Good. Now at this point, we have a tetrahedroimmediate with a good leaving group. Let's kick our H plus down, kick out our alcohol. We get to our final product here, which is a ketone plus isopropanol. So we've generated methanol, which is from there, or ethanol and isopropanol from there, and then we remake the ketone. So we've done a lot of work going from ketone to the acetal. This is just taking the acetal and turning it back into the ketone or aldehyde. So this is kind of the reverse of this. All right, another good retrosynthetic problem to work on. Okay, so there we have our problem. So we got to look at this and do a retrosynthetic analysis. So first thing, let's look at what changed, what's been added. So have we added any carbons?
Yes.
Yes. How many carbons do we add? 3. There you go. 3 C's added. Do we add a new functional group? What kind of functional group is it?
Alcohol.
What kind of alcohol? We added tertiary alcohol. Good. And it looks like somehow we need to turn, right? If I number these, let's number some carbons. So let's number them 1, 2, 3, 4. This is 1, 2, 3, 4. And if I say 5, 6, 7, what new bond do we need to make between which two carbons? 1 and 5. So if you look at the starting material, that means we need to something needs to happen with the bromine, right? Something needs to happen with this bromine. But if you look at the starting material, carbon 1, is carbon 1 delta plus or delta minus? Carbon 1 right now is delta plus. We need probably, but if you look at carbon 5, what's carbon 5 in the product? Is carbon 5 delta plus or delta minus, you think? Delta plus. Well, how the heck, wait a second, right? So if carbon 1 is delta plus in the start materials, right? So C1 delta plus in the starting materials, but C5 is delta plus in the products. What do we need to do to C1? C1 needs to be turned into what? Delta plus? Can it stay delta plus, or we have to make it delta minus? We have to make C1 delta minus, right? So need to make C1 delta minus. Do you see that? Because that's the bond we have to make, right? That's a new bond there. So how are we going to make C1 delta minus? What would C1 have to be? Well, let's work backwards. So if that's the bond we want to break, right? We have tertiary alcohol. Tertiary alcohols can come from what kind of reactions? So that's one of the things we looked at. Aldehyde has a CH, so aldehyde has to be a ketone. Ketone in the Grignard, right? A ketone in the Grignard. So what ketone would this have came from? A 3-carbon ketone. What kind of ketone would it have came from? It'd have to be just good old acetone, right? 6, 5, 7. Everybody see that? And if carbon 1 needs to be a Grignard, right? So carbon 1 needs to look like MgBr like that, right? 1, 2, 3, 4. There's a problem. What's the problem?
You have to make it.
Yeah, we have to make it. But there's a problem just inherently right now if I'm looking at this, right? This is a Grignard, so that's carbon 1 C minus. That's acetone. That's a good electrophile. But are there any other good electrophiles in the reaction mixture right now? What is it? What's the problem? We have a ketone right here too. This could find another molecule of itself, right? This Grignard, it probably won't make a 4-membered ring, but it certainly could find another molecule of itself. So we need to do something called protect this. Make this less reactive. And you guys already know how to do that, you just didn't realize it yet. Not an OH. Remember how we make these acetals? If we turn this into an acetal, right, we can make it less reactive. So remember what an acetal looks like. So this would have had to be, so we'll keep it as the Grignard, that's fine. But this would have to look like this. Now it's an acetal, and we call that a protected ketone. So now now this carbon all of a sudden, right, isn't so delta plus. It's pretty sterically hindered, right? Now it's tertiary. There's 4 things on it, right? It's tetrahedral, so it's going to be pretty sterically bulky. Now this isn't that reactive. So we have to put this on first. Right, the very first thing we need to do is put this on. And then we can add the Grignard and all those kind of things. That makes sense? So the first thing you'd want to do is do just that. You need to use some H+, right? Obviously equilibrium arrows. And you need to use this alcohol. All right? And that would get you, right? The bromine's still there. That would get you the acetal, which is the ketone essentially protected. So now it won't react like a ketone anymore because it's something different. So it's not going to be as prone to nucleophilic attack. And then you can add your Mg and ether. That gets you to the Grignard. And then once you have that, you just add in, right, the acetone. That's good. And then you also need to finish it off with H+ and some water, or H3O+, because then that takes the, right, we just did that reaction, where we can take the acetal off with H+ and water, and would also protonate the oxygen from the Grignard reaction. Right, remember acetal, this can be deprotected with H+ and water, that's the reaction we did earlier. Right, another retrosynthetic problem. And that came from this nitrile. Good. So again, we look at these and we need to say, like, how many carbons do we add? Or what have we added? We've added, have we added any carbons? Or we can number our carbons. Let's number our carbons. 1, 2, I'm going to make it simple. I'm not going to do the ring. 1 and 2. So it looks like there's 3 new bonds to carbon 1, right? Carbon 1 also has an oxygen bond and 2 methyls bonded to it. 2 methyls, that's interesting. Okay. Somebody should be thinking about that. And then we also have this acetate group on there as well. Okay. So which bond do you think is the weakest bond in here, the most likely bond to break first? So it could either be C1 and O, or O and 3, as I have it marked here. Now, if you were thinking, right? I mean, I guess in this case, you could do it either way. I could see multiple ways to do this. All right. Now they're going to hinder you the way they want you to do it. The way they're going to want you to do it is to have this be the bond that you break. Right? But this is an ester. Do you guys know how to make an ester? What can you make an ester from? Think about Mount Carbonyl. What's more reactive than an ester? An acid chloride, right? So this could have been OH, and this could have been an acid chloride. Another thing to think about, like why choose it this way, right? 1, 2, 3. So why not break this bond? So carbon 1 is what kind of carbon? How many carbons is carbon 1 bonded to? It's tertiary, right? We've done a lot of SN. Right? Is it easy to do things on tertiary carbons? Right? Can you do an SN2 on a tertiary carbon? Right. So if you can avoid having the tertiary carbon, right? Because you'd have to say go through an SN1 and a carbocation. Do we want to have carbocations usually? No. So that's another way to think about it. Is like let's choose away from the part where we have a tertiary carbocation or right, a tertiary carbon bond. That's harder to make. Okay, from here, so acid chloride we can make. This looks like a tertiary alcohol, right? This looks like tertiary alcohol. What would that have came from, do you think? Not necessarily. It could have came from acetone, right? So there's two ways. Again, there's multiple ways to do this. They want you to think about it as, right, starting with an aldehyde here. And there's a reason why, if you go back to this nitrile, because we have to go through the nitrile. But here they're going to say, I want it to come from this aldehyde, right? Because one of the options here is to add, there is no option to have a cyclohexyl grignard. That's not one of your options. So that can't work, right? Otherwise, acetone will be just fine. Everybody understand what I'm saying? That if we had a cyclohexyl grignard, that would work. But our options, the only two grignard options we have are methyl grignard, which we need 2 of these, right? Or ethyl grignard, which doesn't work. Right? So we have to go through this way. On a test, you could have gone through you could have done it the other way, for sure. Okay. Keep working back here. So now, where does this come from? This aldehyde. Or wait a second, is it an aldehyde?
PCC.
Maybe it shouldn't be an aldehyde. What else could it be? Well, wait a second. Can it be an aldehyde? Let's think about this. Am I wrong? What did I do wrong? I did something wrong here. Definitely did it wrong. What did I do wrong? It can't be an aldehyde, can it? Right? Because if I use an aldehyde, how many grignards would I add? Just 1. Right? And I need to add 2 methyls. So what does this need to be? It can't be an aldehyde. What does it need to be? Ketone. It could. But do you know how to turn an ester into a ketone? Do you know how to turn an ester into, or a nitrile into an ester? I think you do. You did it in the Keck project. Right? But an aldehyde won't work there. It has to be an ester. I need to add 2 methyl grignards. And if I had the aldehyde, I'd only add 1, right? That's my mistake. You need to have an ester there. Can you turn a carboxylic acid into an ester? Keck project? Yes, you can, right? So usually you have to go through a carboxylic acid to do this. And an ester and a nitrile can be turned into a carboxylic acid. A lot of you guys did this in one pot, which you could as well. So moving forward, you definitely need H+, right, to activate the carbon of the nitrile. And they say use water, right, and that would get you the carboxylic acid, but you could have just immediately used methanol too. Right? Instead of having this extra step where you say H+ in methanol. Right? You could have just kept going. And instead of having water, had methanol in there from the very beginning. But they want you to go through 2 steps. Grignard adds, right? We had 2 methyls. These 2 methyls come from this. These 2 add together. No need for a catalyst. This is reactive enough that they'll react, and we'll also make the other byproduct in here would be HCl. Right, so the way to remember this or to think about this problem is to think about, okay, what should you have learned from this? You learned a way to make an ester. What do you make esters from? You can make esters from nitriles if you put H+ in water and then do H+ in an alcohol. Whatever alcohol you want, you can make that into an ester. You can make carboxylic acids from nitriles. right? Just H plus and water. Right? That's what you should remember from this problem. And if I want to make a tertiary alcohol that has two of the same things, that can go through an ester as well. But we need two equivalents of that Grignard. So there's three take-home messages I would say from this. How do you make an ester from a nitrile? How do you make a carboxylic acid from a nitrile? How do I make a tertiary alcohol with two of the same things? Also from an ester, right? Think about these products and what they came from. That's the big take-home message from this. So when you're working on these problems online, these retrosynthetic problems, after you get them, or if you do not get them, or well, after you get them, make sure you click on the explanation tab. Because the explanation tab will show you all the intermediates. It usually says what happens in each step, right? So it's not necessarily, right, when they have these little boxes, they don't show you all the intermediates, but in the explanation, they'll show you all the intermediates and exactly what's going on. So it's good to look at that too. Okay. Kind of a blowout scheme here. We'll handle these individually. So if I want to take a secondary alcohol and turn it into a ketone, what do I need to do? What kind of reaction is this? Alcohol to ketone is an oxidation. So probably chromium. I mean, actually, in this case, you could use everything. You could use chromium, you could use the bleach, you could use PCC. It takes one alpha CH. Good. Now, if I want to take this and turn it into a tertiary alcohol, that tertiary alcohol, what do I need to add here? Not a reducing agent, but a Grignard, right? And which kind of Grignard do I need to add here? I've added methyl Grignard, right? I've added one carbon, I need to add methyl Grignard. And of course, at the end, you got step 1, and then you need to add a step 2 with either H plus or water, right, to protonate the alcohol. All right, that's methyl. Now they're saying, what's going to happen if I treat this with H2SO4? What am I going to make? I'm making alkene. Which alkene should I make? Hopefully the most substituted one. So we need to look for an elimination here, right? And so that means you need to look for what H's? Not alpha H's, but beta H's. How many types of beta H's do we have here? One, and then 2 types, right? And which one are we going to take? Probably the one in the ring to make the more substituted alkene. Good old Zaitsev's rule, right? And then they say once you have that, okay, now we're going to treat this with BH3 and H2O2. And what does that do? Who remembers what that does? That gives the anti-Markovnikov product. So where on the alkene would it be? Which carbon? The more substituted, less substituted one? Where the OH going to end up? End up in the less substituted one. Good. And of course, that's a cis addition, right? We could also add that in here. Remember that this would be going back and there'd be an H that was added also going back, cis addition. And then they're saying, okay, now that you have this, how would you turn that into this ketone again? What would we need to use to turn it into a ketone? We could say PCC, chromium, any of those things, right? Anything is, all those are possible agents, right? I think they're using just chromium. All right, now they say again, now they're saying, well, what if we want you to turn that into this? What are you going to need to do? Grignard again. What kind of Grignard? Methyl Grignard again. So that's one. And then we need to add water at the end, or H plus, to make the alcohol, right? Because we have an O minus, we need to protonate it. By God. They're saying H2SO4 again. Now, which way do you think it's going to go? What kind of alkene are we going to make? You need an elimination. We'll make the most substituted alkene we can. There we go. And now it says you're going to add O3. Well, what does O3 do? O3 clips down the middle, right? So we don't lose any carbons. But what was the alkene now has, and make sure we number our carbons right, 1, 2, 3, 4, 5, 6, 1, 2, 4, 5, 6. I didn't lose any carbons. That's good. And that's it. And that's our merry-go-round. There we go.